Every headline in astronomy hides a patient story, and it asks us to listen for what changed between last year and this week, as if the universe were leaving careful notes on our doorstep. We hear of a black hole whose ring of light has shifted with time, and of a distant planet whose air seems to hold a new mix of simple molecules. And we wonder not just what those facts mean, but also how they make a person feel. We read that gravity can shove a newborn black hole like a hard goodbye, and that ripples in space-time can tell us which way it fled. And we notice how a single measurement can turn a faraway event into something strangely personal. Tonight, we lean toward fresh findings that still feel warm from the instruments, and we ask how these pieces change the way we hold our lives from moment to moment, because news from the sky is also news about us. Welcome to the Drowsy Astronaut. Here we drift deeper into the cosmos, while gently setting aside the troubles of your day, so you can relax, or even fall asleep while your subconscious wanders through the latest discoveries, the recent findings that remind us the universe is still unfolding quietly all around. I wish you a deeply relaxing journey as we settle into this gentle exploration. Now let's begin. The first thing to know is simple, and it helps everything else feel less sharp. When telescopes report a result, they are reporting a change in our shared understanding. Astronomy does not race like breaking sports, and it moves like patient tide that climbs one step, then rests. Yet each careful step can open a door in how we picture the cosmos. We can think of discovery as a whisper that asks us to adjust a picture on the wall and to straighten it by a small angle, and over time those small corrections can make the whole room feel new. Stories like these are not just technical, they are small letters to our future selves, saying that reality is still larger than our habits. Let us start with the black hole that became an icon, the one in the giant galaxy called M87, where the Event Horizon Telescope stitched a ring of light from radio waves. In the newest analyses that reach us this week, researchers saw the pattern of polarized light subtly flip over different observing years, a sign that magnetic fields near the hole can re-thread themselves like braided rope. That ring we all remember is not a museum statue, and the environment around it is alive with fields that tug on matter, twisting charged particles into a jet, and then surprising us by changing direction in the polarization map. Seeing a flip like that makes the picture breathe, because it tells us the engine is not static, and our models must flex with it, and that feeling of motion wakes up a human kind of curiosity. If the word polarization feels far from home, try a sink with swirling water and a small leaf that keeps the same tilt as it rides the current. The way that tilt lines up tells you something about the flow you cannot see. Light near a black hole can also line up, and that lining shows the hand of magnetism. So when the alignment flips, the invisible scaffolding near the hole has likely changed. We are not watching the edge of the hole itself, we are reading a thin fog of hot plasma, and its behavior writes delicate notes in the light that reaches us. Step by step, such notes let us test how gravity and fields share the work of shaping the jet, and that is how a photograph becomes a living instrument. There is also the black hole at our center, the one in Sagittarius A that looks small but near, where teams have been pushing toward clearer frames and even time-resolved movies. To a person hearing this while washing dishes, the word movie might feel oddly fun, and it is earned, because with more stations and better bandwidth, the telescope network can catch motion rather than only a still. Imagine a candle seen through rippling air and trying to learn its shape from brief, steady moments. That is the challenge near our own black hole, where things change faster than our exposures. Progress toward movies matters because motion tests ideas that still images cannot, and it brings us closer to watching gravity do its work in real time. Now we drift toward planets around other suns, and we look at their skies the way we sniff air near a kitchen window, wondering what a single breath of data can really tell us. In one rocky world that sits in a gentle zone, teams with Webb have hinted at a possible atmosphere, not a loud claim, but a cautious sign that air may cling to a place not much larger than Earth. Hints are not proof, and that word is a gift because it keeps us from running ahead of the evidence. Yet even a hint changes what we can hope to learn next. Some nights you read the same sentence twice and feel a small lift because a potential atmosphere on a rocky neighbour widens the circle of places to imagine. You may have seen headlines about TRAPPIST-1e and how its air might look more Earth-like. The careful truth is that teams are still sorting signals from noise and weighing different models. The instruments are strong, but the targets are faint, and the light we collect passes through layers of complexity. So we rely on patience, cross-checks, and the humility to move one rung at a time. There is a comfort in slow work, because it protects meaning from wishful reach, and it lets the result survive the next reanalysis. Either outcome teaches us, because recognizing a false alarm is also knowledge, and it sharpens our tools for the next faint planet. Another story that moved hearts was K2-18b, a world larger than Earth but smaller than Neptune that sits in a zone where liquid water could be possible, with methane and carbon dioxide reported, and then questions about a molecule tied loosely to life. A new study this summer pulled gently on those claims and found no firm sign of that special biosignature, which is both sobering and helpful because science breathes best when it trims its own sails. Think of a friend tasting tea and saying there might be vanilla, then later saying it was likely just the cup. The honesty of the correction is part of why you trust their next description. Care like this keeps the field healthy, and it lets us love the search without tying our hope to any one interpretation. Some teams look at wildly different worlds, including candidates near dead stars that spin like cosmic lighthouses. And early Webb analyses have even floated exotic ideas about unusual atmospheric makeups. When you read that a pulsar planet's air could be almost pure carbon, you can hear the word could. And that small word is the seatbelt we wear on the ride. We test bold claims against better data, and we keep the wonder while guarding the method. Because the point is not to be first, it is to be right in the long run. Still, the act of checking teaches us about instruments, about models, and about the clever ways nature can surprise us. Gravitational wave observatories offered a fresh note this month, a beautifully clear detection that lined up with a theory from Hawking about black holes, adding weight to a rule about event horizons and how they behave during mergers. You can feel the human joy in a result like that, because it closes a loop between pure thought and the shaking of space-time that we can measure. It is like planning a route on paper, then walking the street and finding the landmarks exactly where the map predicted, a quiet fit between mind and world that restores a basic faith. Proofs in physics are not courtroom proofs, they are layers that settle into place, and this is one of those settling layers. Another headline described the kick given to a newborn black hole, a shove from the imbalance of a merger, measured directly from the shape of the gravitational wave signal. If you have ever held a door and been pulled forward when someone else let go, you know how unequal effort can leave a sudden motion, and the cosmos does that at scales that turn metaphors into numbers. A recoil that can fling a black hole free of its cluster feels like drama, yet it is just the math of asymmetry, translated into speed by curved space-time itself. Measurements like this let us picture the aftermath, and they answer a simple human question about where the remnant went after the embrace. Closer to home for many of us is radio astronomy from India's Great Telescope Array, where a rare millisecond pulsar was found in the dense stars of Messier 80, a discovery that turns the cluster into a new lab for gravity. A pulsar is a spinning star with a beam that sweeps us like a metronome, and timing those ticks in a tight orbit can reveal how relativity bends time. When the orbit precesses by half a degree per year, the system becomes a chalkboard where nature writes neat equations, and we get to read them with the leisure of a long afternoon. Findings like this expand the toolset we can use to weigh masses, to test theories, and to sketch how stars evolve in crowded swarms. If all of this feels like many threads, you can hold them with a single image: a person at a window watching changing weather, clouds that move, sunlight that shifts, and air that carries a hint you cannot yet name. Each result is a moving cloud, and together they change the tone of the day, not by shouting, but by leaning the light a few degrees one way or another. The black hole's magnetic flip is a gust, the exoplanet hints are a thin scent, and the gravitational wave conformations are the firm edge of the horizon clearing in view. Discovery is therefore not one loud event. It is a practice of staying with the details, long enough to feel how they alter the room of the mind. You might ask what this means for you, which is the only reasonable question for a midnight listener, because a fact that does not touch life is only half alive. One answer is that fresh cosmic news can teach a softer posture towards stubborn opinions. If a ring of light can change its pattern, perhaps our own fixed ideas can budge as well. Another answer is that patient method pays off, and that is true for budgets and relationships, for anything that grows better when kept steady. Finally, there is the emotion itself, a quiet rise in the chest when we see a new picture and recognize that the universe still has room for our curiosity. Let us return once more to the ring in M87, because emotion without detail is only a sigh, and detail without emotion is a chart we will forget. The polarization maps trace fields that shepherd hot matter, and a reversal over years suggests a living engine, where turbulence, rotation, and magnetic tension rebalance. In plain words, this means the neighborhood near the hole is busy, and that the donut of light is a moving story, not a logo stamped forever on a poster. Knowing this shifts how we talk about the image to children and to friends. We stop saying it is the black hole and start saying it is a radiant footprint of surrounding matter. On the exoplanet front, think of spectra as barcodes of light, and of an atmosphere as a shop that removes certain lines, because molecules absorb at their favorite energies. When Webb reports methane or carbon dioxide, it is reading those missing lines like a receipt, and arguing about a biosignature is partly arguing about how clean the receipt was. The newest careful work on K2-18b says the exciting molecule is not yet firmly there, and that is a kindness to the future because it keeps hope from running past evidence. Meanwhile, the tentative hints of air on a small rocky world keep the door propped open for the kind of place many of us dream about. With gravitational waves, we learn to hear by feel and to let an instrument pass music from space-time, where the pitch and rhythm tell us masses, spins, and even recoil. The clear test of a theory about horizons turns argument into a measured curve. And there is a deep peace in seeing an old idea survive a new tool. If you have ever built a shelf and pressed on it to see if it holds, you know the pleasure of sound structure. Physics offers the same simple contentment when the world does what a good equation predicts. Add the natal kick measurement, and we are not only weighing the dancers, we are watching the last step fling the pair into the hallway. Each discovery also teaches us how to wait, which is a skill in short supply, and how to hold wonder without gripping too hard. Because instruments improve, collaborations grow, and patience turns noise into knowledge. When a telescope array upgrades a dish here and a receiver there, it is like sharpening a pencil. The lines get cleaner, and the shading can show motion we once blurred away. When an analysis pipeline learns to catch systematics before they spread, it keeps a small error from becoming a big headline. If you want one image to carry into sleep, consider the way a person keeps old photos in a box, and every few years they open it and see the faces with slightly different eyes. The sky is our oldest album, and every new result changes how we read a familiar page. Not by erasing the past, but by adding context around the smile of a galaxy or the frown of a spectrum. This is why late-night reading of astronomy can feel like tidying a room, because a small fact straightens a frame and settles the mind. Tomorrow you will move through errands with the same body, yet the world will feel a little wider because the map grew new edges. Let us set one more anchor in clarity, because soaring words feel better when their feet touch the ground. The EHT's polarization flips are about magnetic field geometry changing across campaigns. The exoplanet atmosphere hints are about faint signals teased from light filtered through alien air, where false positives are common and caution is strength. The gravitational wave results confirm old principles while adding details like recoil speeds, and those speeds connect to where the remnant can live. These are the bones under the story, and bones are what let a soft narrative stand. We close this stretch not with a summary, but with a steady breath you can carry into the next hour, because the news will keep arriving, and your curiosity will keep making room. There will be more frames of our center, more careful reads of distant air, more quiet confirmations that ideas we trust can hold one more weight. Between such updates, your life will keep its chores and comforts, and the sky will keep its deep patience. The black hole stories linger in our minds, not just as technical notes, but as reminders that our instruments have reached into the most silent regions and managed to bring back signals that human eyes can finally read. When you think about the M87 ring, it is tempting to freeze it as a finished image, a neat symbol, but the newer evidence asks us to see it as an evolving pattern, alive with shifts that tell us of a restless engine. That restlessness is not a flaw, it is the truth of matter that swirls near the horizon and of fields that twist and bend under strain, because the universe is never still, and every structure holds change inside it. Motion is the story behind every snapshot, and stability is only a pause we use to understand what was caught in the frame. The environment near a black hole is not a quiet museum, it is a furnace where particles accelerate to near light speed, and their motions carve luminous scars in the radio light that crosses millions of years to us. To grasp it in plain words, imagine a storm on Earth with winds spiraling faster than a jet and magnetic ropes threading through the sky. The difference is that these winds carry near infinite energy, and the ropes are made of invisible force. Each adjustment of the polarization map is a hint about how those ropes twist, and how the plasma organizes itself as it spills outward into the jet. Learning from these hints is slow, But with each new observation, the hidden forces of magnetism and gravity appear less like mysteries and more like friends whose moods we are beginning to read. Let us shift from that massive furnace to the quieter heart of our own galaxy, because Sagittarius A is less dramatic in size, but far more intimate in the way we watch it. Our Milky Way's central black hole is only a few million solar masses, while M87's is billions, and that scale difference is what makes our view both harder and richer, because the smaller object changes more quickly and its light flickers faster than we can always catch. This flickering is not noise, it is a heartbeat of matter as it dives toward the center, and every pulse is a page in a book we are still learning to read. Researchers are stitching those pulses into moving frames, and someday soon we may be watching time-resolved videos of matter orbiting before vanishing. The idea of such a movie is more than novelty. It carries an impact that still photographs cannot, because motion reveals cause, and cause makes the story less abstract. Think of how you recognize a friend not only by their face, but by the way they walk. The stride is as telling as the static features. Motion near a black hole is the same, and a flicker of orbit, a flare of plasma, a sudden dimming, all these are gestures, and they let us know the object in question is not an icon, but a living furnace. Step by step, these gestures connect the extreme physics to our everyday sense that movement reveals character. The telescopes we build are not just machines, they are collective eyes, linked across continents so that their separation grants resolution impossible for a single dish. The Event Horizon Telescope is a prime example where stations from different parts of Earth become one aperture. The timing and synchronization are so precise that the rotation of Earth itself becomes part of the lens. It is hard to imagine the patience and detail of aligning so many instruments. But the result is the ability to read details as fine as a credit card lying on the surface of the moon. Scale like this is both humbling and empowering, because it shows that even fragile humans can build tools to see across incomprehensible gaps. From the horizon of black holes, let us drift back toward planets and toward the light that passes through their skies, because exoplanet atmospheres are where discovery and hope entwine. The Webb Telescope has already given us new spectra, barcodes of absorption lines that whisper of gases like methane, carbon dioxide, and even water. And each spectrum is a quiet vote that life elsewhere is not impossible. Yet every bold claim must bend to caution, for molecules like methane can rise from volcanoes, and carbon dioxide can appear without biology. So the work is less about shouting proof and more about weighing balance. Science is most honest when it tells us what it does not know, because the humility protects the wonder more than exaggeration ever could. Think of how you smell a faint scent of smoke and wonder whether it is a campfire or just a stove. That is the level of subtlety astronomers deal with when interpreting spectra. The lines in light are not labels on bottles, they are gaps where atoms drank specific photons, and those gaps are hard to tell apart when the source is faint. What matters is not only what is there, but what is absent, and whether the absence is clean or muddied by noise. And this is why careful reanalysis can overturn earlier excitement. Corrections may sound disappointing, but they build a stronger bridge, and they make the eventual discovery stand on firmer ground. We should remember that planets like TRAPPIST-1e and K2-18b are not pictures but points of light, and we rely on physics to unfold those points into atmospheres. When we hear of methane on K2-18b, we are not smelling the gas, we are reading its signature. and the difference between an illusion and a reality can hinge on calibration. This work demands an attitude of patience, a willingness to sit with numbers and sift error, much like a sculptor removes stone until the shape appears. Discovery is then the shape that remains, while assumption is what was chipped away. Even so, each cautious step forward changes the way we imagine our place, and that is what matters most, because possibility reshapes our sense of loneliness in the cosmos. The knowledge that another rocky world may hold an atmosphere shifts not only science, but also our private dreams. We picture oceans, clouds, and skies where life might breathe. We will not meet such neighbors soon, but we carry them in our thoughts and we carry them in our evening walks, because even the hint of company changes the silence. Silence, in this case, is not absence, it is an invitation, and hope is the voice that fills it. Meanwhile, gravitational waves keep whispering of mergers, and each new detection ties theory closer to reality, turning chalkboard sketches into confirmed ripples in space-time. The natal kick of a hole formed in a merger is not just a curiosity, it is a measurement of how symmetry broke. And symmetry breaking is the very essence of how structures form. If a black hole can be flung out of its cluster, we are watching cosmic exile, and that motion echoes the imbalance of smaller things like atoms. Balance is rarely perfect, and imbalance is the engine, whether in the physics of gravity or the lives of people. Think of a dance where two partners do not move with equal weight, and the floor receives the recoil. That is the image of a gravitational wave's asymmetric shove. The waves carry not only energy, but direction, and their form encodes the recoil, speed, letting us say not only what happened, but also where the remnant went. This is storytelling at the deepest level, a story written in space-time curves rather than on paper pages, but still readable with instruments trained to listen. Listening here means filtering vibrations smaller than a proton's width, and that feat reminds us of the precision humans can reach. Even neutron stars and pulsars extend this story because their timing becomes a measure of relativity, and their spin tells us of the strength of matter under pressure. Millisecond pulses in crowded clusters become more than curiosities. They are clocks that let us watch orbits precess and time stretch, each tick adding another layer of evidence that Einstein's equations hold. The most patient work is often the most profound, as each degree of precession builds toward a verdict on theory, and each tick tells us the clock is faithful. Patience is the secret thread that ties radio pulses to cosmic truths, for without waiting, the rhythms would only look like noise. Each of these findings, from black holes to distant air, from gravitational waves to pulsars, has its own weight, but together they weave into something greater. They tell us the universe is not still, not finished, but alive in change, and we are part of the change simply by being able to see it. The act of looking is not passive, it is an act of joining, and the act of listening is an act of care, because when we attend to reality, it speaks more clearly. Joining with that voice is what astronomy gives us, not just knowledge, but a deeper companionship. So let us move forward, deeper into this quiet night, carrying the latest discoveries, not as trophies, but as companions, because they help us walk more gently in our own world. The sky's lessons are not only technical, they are mirrors in which we can see our habits, and in noticing their limits, we gain the freedom to shift them. Every flare near a black hole, every faint exoplanet signal, every tiny gravitational ripple, every tick of a pulsar's beam, all of them lean quietly against our daily routines. Next, we will follow more of those signals into corners of the cosmos where questions still wait, and let them teach us to hold both patience and wonder in the same breath. The black hole that we left behind is not silent, it is a mirror for our imagination, and each year of observation adds one more brushstroke to the picture we thought we already knew. It is easy to think of science as a library where facts sit still, but the truth is that even the most famous images change quietly behind the scenes, and their updates carry as much meaning as the first reveal. Consider how the ring in M87 has shifted in its polarization and how the patterns of magnetic fields refused to stay locked, reminding us that the engine of matter and light near the horizon is alive. Alive here does not mean biological, but it means dynamic, and dynamic is the rhythm that makes every discovery worth hearing. This is why researchers are now working on a movie of Sagittarius A, the smaller black hole at our own center, because the flickers of light near its edge change too fast for still photographs. Imagine watching a candle through moving air and realizing that every stable frame hides a restless flame. That is the challenge of building time-resolved frames of a whole that shifts every minute. Each pixel is a heartbeat, each burst of plasma a gesture, and soon we may see those gestures stitched together into moving sequences. Watching such a movie will not only confirm models, it will let us feel that even the deepest gravity has a pulse. We can already glimpse progress, with instruments linking across continents and receivers gathering finer threads of light, and it is like weaving a tapestry from thousands of hands at once. The Event Horizon Telescope shows us how patience becomes power, and how global collaboration can turn Earth itself into one eye, an eye sharp enough to read the glow of matter at the brink of falling in. When that eye sharpens further, Sagittarius A will no longer be a still icon, but a flickering story, the first moving portrait of a black hole in human history. This is how discovery grows, not in leaps every day, but in steady years of tuning dishes and timing signals until clarity appears. From the black holes, let us drift outward toward planets, because Webb's latest results speak not of collapse, but of air and possibility, thin traces of gases that might wrap themselves around distant rocks. The telescope has measured spectra from worlds like K2-18b, where methane and carbon dioxide appear, and whispers of a rare molecule once hinted at life, though new analysis softens that claim. Still, the idea that light passing through alien skies can tell us their contents is itself extraordinary, and the care with which scientists withdraw bold claims is part of the honesty that makes the field strong. Corrections are not failures, they are guardrails, and guardrails keep our wonder from tumbling into confusion. In TRAPPIST-1's system, rocky planets keep circling their faint red sun, and Webb has begun to test whether their air holds on or slips away. Some results are still inconclusive, yet even inconclusive findings guide the next steps, narrowing which models survive and which ones fall aside. To a listener late at night, the difference between signal and noise may feel abstract, but it is the same as hearing a faint knock on a door and waiting for it to repeat before you open. Patience with those faint knocks is why the field will not shout too early, and patience is also why the eventual confirmations will matter deeply. Another recent highlight comes from gravitational waves, those faint ripples in space-time that pass through Earth, detected by LIGO, Virgo, and CAGRA as they vibrate mirrors with precision beyond human intuition. One event revealed the kick of a newborn black hole, as asymmetry in the merger shoved it in a chosen direction, a recoil strong enough to fling it away from its star cluster. Think of pulling a door unevenly and being tugged when the hinge fights back. The cosmic version of that motion is written in the shape of the wave. Recoil may sound like drama, but it is also the plain mathematics of imbalance, and imbalance is the reason the cosmos does not rest. Other events test theory in subtler ways, confirming Hawking's predictions about how black holes behave, showing that horizons are not just metaphors but rules that survive even violent collisions. To know that a pure idea scribbled decades ago can meet a signal from billions of light years away is one of the quiet joys of physics. It is like tracing a map long before you walk the street and finding the landmarks exactly where the ink promised, a confirmation that thought and nature were walking together the whole time. Confidence like this does not end the mystery, but it deepens it, because surviving tests means the theory is strong enough to guide us further. Meanwhile, radio astronomers in India have found a new millisecond pulsar in the star cluster Messier 80, and its precise timing has already given clues about relativity. This pulsar's orbit precesses by 0.5 degree per year, a tiny motion that becomes a giant signal when tracked over seasons. To explain in homely words, imagine a clock that ticks slightly differently each day, and through its ticks reveals the bending of time around it. Reading that clock is not just astronomy, it is listening to nature set down equations in rhythm. Each of these discoveries arrives like a letter, but the letters make sense only when placed in the pile together, building an evolving narrative. A narrative where black holes change, planets breathe, waves shake, and clocks stutter. We may think of science news as separate items, but in truth they are chapters, and each chapter only makes sense because of the ones before and after. The shifting polarization in M87's ring, the methane corrections in K218b's spectrum, the gravitational kicks, the pulsar precession, all of these threads weave into a single growing fabric. Fabric is the right word, because what we are seeing is not fragments, but a cosmos held together by laws that remain steady even as details shift. Yet beyond the detail, there is the dreamy side. What does it mean for a human life to listen to signals from places beyond reach, to lie in bed and let those faint reports seep into thought? It means that curiosity is not just intellectual, it is emotional, and discovery is not just data, it is comfort. Knowing that somewhere a planet breathes or a black hole flickers steadies us against the idea that everything familiar is all there is, and it opens a space inside where our imagination has room to wander. Wandering itself is a gift, for in wandering we find new views, and in those views we find quiet companionship with the sky. The balance of technical and personal is exactly what makes astronomy both difficult and worth it, because each measurement must be hard, while each conclusion must still touch our lives. A signal too faint may be noise, and an interpretation too bold may be wrong. Yet even false starts shape the careful path forward. We remember claims of biosignatures that softened, and we remember proofs that held firm. And the rhythm of correction and confirmation is what makes the field breathe. Breathing like this gives science its humanity, and humanity is why the discoveries matter beyond the numbers. The universe itself is not standing still, and the most profound discovery of the last century was that galaxies are moving apart, carried by invisible space. And this realization continues to echo through every corner of modern astronomy. What Edwin Hubble once measured with careful spectra of galaxies has now been confirmed and deepened by satellites and the Webb Telescope. Yet the question of how fast the universe expands is not settled. The Hubble constant, that simple number meant to define expansion, is still uncertain by more than one margin, because local measurements and early universe measurements refuse to agree. Disagreement here is not a flaw but a clue, and clues like this may point to physics we do not yet know. Imagine watching two clocks, both of them steady and precise, but giving slightly different times. One clock tells you the early universe's story, the other tells you the story of galaxies today. The early clock is written in the microwave background, that faint afterglow of the Big Bang, while the other is calibrated by stars, supernovae, and galaxies closer to home. When these times disagree, the safe answer is not that one is wrong, but that something deeper in our model is incomplete. And that incompleteness is itself a discovery. Expansion then becomes not just a number to calculate, but a puzzle that keeps scientists awake, and a puzzle that gives listeners a reason to lean closer. Recent results with the Webb telescope have refined distances, especially with Cepheid variable stars, those bright beacons whose flickering brightness reveals how far their host galaxies stand. Each correction adds detail, yet the tension between early and late universe measures remains, and that tension might be telling us about new forms of energy or unseen physics. It could be an unknown particle slipping through the gaps or a new interaction between matter and dark energy, or it could simply be that our instruments need still finer calibration. Either way, the tension makes the universe more alive, and either way, the question itself has become part of the story. Dark energy itself remains the great mystery, a pressure that stretches space faster and faster, as if the cosmos were pulling against its own gravity. To explain in simple words, think of throwing a ball upward and expecting it to slow, only to watch it speed away. That is the shock astronomers felt when expansion was found to accelerate. This acceleration was first measured through supernovae, those bright stellar deaths used as cosmic candles, and the discovery won a Nobel Prize because it rewrote our understanding of fate. Fate here means the destiny of everything, and the presence of dark energy shifted that destiny toward eternal stretching. Recent surveys keep mapping galaxies in 3 dimensions, tracing how structures grow and measuring how gravity competes with expansion, and the latest data still point toward dark energy as the ruling term. Even the subtle ripples called baryon acoustic oscillations are used as rulers to check how fast expansion has gone at different epochs. It is not that we know what dark energy is, but that we know how it behaves. It behaves like a steady push built into the fabric of space. Fabric itself is a metaphor, but it is apt, for this push stretches every thread, and that stretching is why galaxies drift apart even when they do not move. The cosmic microwave background, that ancient light from when atoms first formed, is another witness to expansion, another canvas where early ripples remain frozen, and those ripples map the seeds of galaxies. Satellites like Planck have measured its patterns in exquisite detail, and from those patterns comes a clear picture of a universe born hot and dense. Yet when those numbers meet today's distances, they clash, and that clash is where new ideas may rise. New physics often comes from such stubborn mismatches, and stubborn mismatches are exactly what keep fields alive. Think of how in daily life you notice a creak in the floor and then realize it does not match the weight you expected. The mismatch is the invitation to look deeper. In astronomy, mismatches between early signals and late signals are not errors to sweep away. They are windows through which a new piece of reality may peek. The Hubble tension is one such window, a stubborn rift between expansion measured by Cepheids and expansion measured by the cosmic background. Some argue it is a calibration flaw, others argue it is new physics. But in either case, it keeps the universe from growing dull. Galaxies themselves are witnesses to this drama. Great cities of stars drifting apart as space stretches, their clusters still bound by gravity, but their long-term fates pulled outward. When we look at galaxy surveys today, we see webs of filaments, with galaxies tracing vast structures that still echo the first density ripples. Recent Webb images of galaxies only a few 100 million years after the Big Bang surprised astronomers by looking mature, already filled with stars, suggesting that structure formed faster than many models assumed. Speed like this unsettles our neat timelines, and it may force revisions in how quickly galaxies built themselves in the early years. These surprises are not failures, they are gifts, because a model that is too comfortable teaches nothing. Only when the picture cracks do we find new paths. The discovery of early massive galaxies may hint at unusual cooling or unknown processes in the first stars. Perhaps the first stellar generations were more efficient than we thought, or perhaps dark matter helped clump them more quickly. Answers are still in play, and until they settle, the questions themselves carry weight. Drifting further, consider the analogy of footsteps in sand, where some are shallow and some are deep, and the tide later fills them. The galaxies we see are like those footprints, revealing both the walker and the wave. The expansion is the tide, and the galaxies are the marks. And to read them, we must understand both forces together. Webb's new images extend this record, showing structures far earlier than Hubble could reach, and their clarity has already forced textbooks to soften claims. Textbooks are not stone, they are sketches, and sketches change when new ink is applied. Another piece of the puzzle is dark matter, which although invisible still makes up most of the mass, holding galaxies together even while dark energy tries to pull them apart. Dark matter shows itself in gravitational lensing when a massive cluster bends the light of galaxies behind it into arcs. Recent lensing maps from Webb have been able to trace this distribution more finely and show clumps of invisible structure nested inside clusters. Nested within, they act like bones under skin, and those bones hold galaxies firm even while space itself expands. This expansion is not a rushing wind. It is more subtle, like the stretching of a rubber sheet where dots drift farther. Not because they move on the sheet, but because the sheet itself grows. To picture it another way, think of a loaf of rising bread with raisins, and each raisin sees all the others drifting away as the dough inflates. What makes the cosmic loaf stranger is that the rate of expansion is not constant, and the acceleration is still unexplained. Unexplained forces often lead to revolutions, and revolutions begin quietly, with data that do not line up. As we listen to these discoveries, there is a personal side. What does it mean that the cosmos is stretching, that all distances grow with time, and that the future promises more emptiness than closeness? It may feel lonely, but it is also honest, because the sky is telling us how it works, and our role is to accept what is revealed. We can choose to see this as loss, the slow drifting away of galaxies, or as freedom, the reminder that everything familiar is only temporary and that transience itself is natural. Natural in this sense is not comfort, but it is clarity, and clarity can still bring peace. Recent updates keep layering onto this story. New galaxy surveys, improved distance ladders, sharper Webb spectra, and each update nudges the numbers while leaving the mystery intact. The hope is that with more data, the rift in the Hubble constant will narrow, or that new physics will step in to explain. Either path is valuable, because in science a question well defined is a victory, and the persistence of mystery is an invitation. Invitation is a softer word than proof, but it suits the mood, for proof ends a story, while invitation asks us to keep walking. Galaxies are not only the evidence of expansion, they are also living cities of stars, and each one grows, collides, and reshapes itself across billions of years. When you picture a galaxy, you may imagine a simple spiral, yet spirals are only one form, and the universe has written countless other designs, from ellipticals like glowing clouds to irregular forms with knots and scars. Each design is not random, but the memory of how gravity shaped it, and the trace of interactions with neighbors that once passed too close. Close encounters are common on cosmic scales, and each one leaves marks that endure for billions of years. The Milky Way itself carries scars, with faint streams of stars stretched out like ribbons, relics of smaller galaxies torn apart by our gravity. And these faint structures show how our home has been built by devouring others. Astronomers have traced the Sagittarius dwarf galaxy, now stretched into filaments, and they have mapped the flows of stars that once belonged to clusters. Every stream is a story of collision, and every arc is a sentence in the autobiography of our Milky Way. And new surveys with Gaia and Webb are sharpening those sentences into readable prose. Reading these arcs is like reading wrinkles in an old face, lines that carry the memory of countless days. Recently, Webb has turned its eye to galaxies in the act of merging, showing tidal tails and streams of gas, structures that stretch across hundreds of thousands of light years. One striking image revealed two spirals locked together, their arms flung outward, their cores glowing with newborn stars, as if gravity itself had triggered a firestorm of birth. These starbursts are the consequences of chaos, and they show that collision does not only destroy, but also create, forcing clouds to collapse into luminous nurseries. Creation and destruction here are the same act, for in tearing galaxies apart, gravity also plants the seeds of the next generation of stars. Our own Milky Way is on course to meet the Andromeda galaxy in 4 billion years, and their merger will write a new shape, likely an elliptical form born from spirals colliding. Simulations already show streams of stars crossing, and the sun itself drifting into a new orbit. The night sky will glow with arcs of light as the two galaxies fold together. It is easy to hear this and feel fear, but the distances between stars are so vast that collisions will be rare. Instead, the encounter will mostly rearrange orbits, and the result will be a calmer but larger galaxy. Some galaxies are even more violent, with quasars shining at their cores, powered by black holes swallowing matter so quickly that light itself blazes across millions of parsecs. Recent surveys have spotted quasars in the early universe, some only a few 100 million years after the bang. Their existence challenges how black holes could have grown so massive so quickly. Did the first black holes form directly from collapsing clouds, bypassing stars, or did they grow from seeds with extraordinary efficiency? Either way, their light now reaches us as a reminder that the first galaxies were not quiet, but already restless and bright. Not all galaxies are crowded, some live in voids, vast empty regions where few neighbors exist, and these lonely galaxies evolve differently. Without collisions, they grow more quietly, and their shapes remain undisturbed spirals for longer. Yet even they carry histories, because no galaxy is truly isolated from the pull of the cosmic web that binds them, and faint streams of gas often still reveal interactions. Void galaxies remind us that diversity exists, and that diversity is itself a product of the universe's balance between chance and necessity. Clusters of galaxies are different again, immense gatherings of hundreds or thousands bound by a common halo of dark matter, their centers filled with hot gas and constant interactions. In such clusters, galaxies can be stripped of their gas by collisions or by pressure, leaving shells of stars that can no longer form new suns. Astronomers call this quenching, the shutting down of star formation, and Webb has found quenched galaxies earlier than expected, suggesting that galaxies can shut down quickly when pressed by environment. Quenching adds another piece to the puzzle, telling us that galaxies are shaped not only by time, but also by neighbors. Recent Webb observations of dead galaxies in the early universe surprised researchers because these systems stopped forming stars far earlier than models predicted, and their very existence forces a revision of theories. It seems some galaxies burn too brightly, exhausting their gas, and then settle into silent ellipticals while the universe is still young. This discovery shifts our understanding of evolution because it proves that endings can come far sooner than we once thought. Endings like these are not final, for mergers can revive activity, but they remind us that life in galaxies is never uniform. Another method of probing galaxies is gravitational lensing, where massive clusters bend light from galaxies behind them, turning faint smudges into visible arcs. Webb has refined these lensing maps, and with them we can see galaxies that would otherwise be hidden by distance. Each lensing event is like a magnifying glass, bending space-time itself into a tool, and each arc is both distortion and gift. Through such arcs we glimpse galaxies that formed when the universe was young, and through them we extend our reach deeper into time. The cosmic web itself is a structure beyond imagination, with filaments stretching hundreds of millions of light years, each filament filled with clusters. And between them lie vast voids of near-nothingness. This web was seeded by the smallest ripples in the early universe, ripples we still read in the cosmic microwave background. And watching it grow is like watching a city rise from the smallest cracks. Surveys today map this web with precision, revealing knots where galaxies converge and rivers of matter flowing between. Flow is the right image because the web is less a grid and more a living network, constantly shaping itself. What does it mean for us that galaxies collide, that they form webs, that they burn out and quench? It means that change is universal, and the same rule that moves galaxies also moves us. Nothing remains as it was, and every end is also a beginning. Recent discoveries only reinforce this lesson, because each new web image of a merger or a quenched system confirms that change is the one constant. Constant is a paradoxical word here because constancy itself is only the constancy of flux. To make this less abstract, imagine your own life, full of small collisions with others, each leaving marks, friendships, arguments, moments of contact that reshape your path. Galaxies behave the same way, with each encounter changing their structure and each exchange of gas altering their future. You are not unlike a galaxy, and a galaxy is not unlike a person. Each one collects stories, carries scars, and grows into a new shape over time. Time is the sculptor here, and time works on galaxies the way it works on us, slowly but persistently. Recent Webb surveys continue to map galaxy formation earlier and earlier, and they keep finding systems that look too mature for their age. Massive spirals and ellipticals when the universe was still in its first billion years. These discoveries raise the question of whether our models missed a step or whether new physics accelerated growth. Did early stars form with unusual efficiency, or did matter clump faster under different conditions? Questions like these are active now, and the answers may reshape our understanding of cosmic timelines. Yet the beauty of it is not only in the answers, but in the act of asking, and in knowing that galaxies far away are still present, their ancient light reaching us now, unchanged by distance. Every Webb image is therefore a time machine, showing galaxies not as they are, but as they were. Each picture a frozen instant from billions of years ago. To look at such an image is to peer into the past and to realize that the present sky is layered with history. History here is not just ours, but the universe's, and each layer is waiting to be read. Stars are the threads that stitch galaxies together, and they are also the anchors of human imagination. For when we look up at night, it is the stars we notice first. Every galaxy is a collection of billions of these furnaces, each one born from gas and gravity. And to understand galaxies, we must understand the lives of the suns inside them. Star birth begins in clouds, immense regions of molecular gas where dust and cold hold matter together. And it is here that gravity begins to gather pieces of a new life. Gathering is the first act of a star's story, and collapse is the word astronomers use when the cloud fragments into denser knots. The Orion Nebula is one of the closest such nurseries, and it glows in photographs because newborn stars are already lighting the gas around them, filling the cloud with light that carves cavities and reveals its shapes. Webb has recently imaged Orion in the infrared, showing details hidden from Hubble, and uncovering tiny protoplanetary disks forming around infant stars. These disks are where planets will someday gather, and their presence so early in life is a reminder that stars and worlds are born together. Together is the key here, for the lives of stars are not solitary, they are bound to the lives of the systems they host. Consider the pillars of creation, an iconic Hubble image now revisited with Webb, showing columns of gas sculpted by intense radiation. The Webb view revealed fine filaments, glowing edges, and hidden stars emerging within. This image is not just beauty, it is evidence of how radiation shapes clouds and of how feedback from massive stars sculpts the next generation. When one star shines, it carves away gas, and when it explodes, it compresses new regions into collapse. The death of one fuels the birth of others. Cycles like this are how galaxies recycle matter, and cycles are why the universe is never static. Stellar nurseries are turbulent places full of shockwaves, radiation, and flows of plasma. And yet from that turbulence emerges steady light that may last billions of years. It is like watching a river full of rapids that eventually smooths into calm, and the calm is the long main sequence phase where stars quietly fuse hydrogen into helium. Our own sun is one such example, midway through its stable life, burning for nearly 5 billion years already, and destined to burn for nearly that long again before it changes. Stability like this is what allows life to form, and stability is what makes stars the clocks of galaxies. To explain fusion simply, imagine two atoms of hydrogen pressed so closely that they merge, releasing a burst. The burst is energy, and multiplied by countless trillions, it becomes the light of a star. The sun turns millions of tons of hydrogen into helium every second, and that process is why Earth is warm and bright. In equations, this looks abstract, but in human terms, it is the steady beat that powers every tree, every breath, every ocean. Every living thing carries that stellar imprint, and every spark of warmth on Earth is a gift from fusion. Webb has even looked into distant clusters of young stars, where the distribution of masses seems unusual, suggesting a different recipe. Perhaps stars form heavier in the early universe than they do today. If this is true, it may explain why early galaxies grew so fast, why their light was brighter than expected. Massive stars burn hot and short, while smaller stars live cool and long, so the balance between them changes how galaxies evolve. Balance here is not random. It is a law of physics, but balance may shift under conditions we do not yet fully grasp. Our Milky Way also hides regions of birth, like the Carina Nebula, now imaged by Webb with breathtaking clarity. In infrared, dust becomes translucent, and hundreds of newborn stars shine through. These images are not only photographs, they are tools that reveal how radiation shapes gas and how winds carve pillars and arcs. The Carina images showed jets blasting from protostars, narrow beams of plasma piercing the cloud, and these jets tell us which stars are still accreting matter. Accretion is a quiet but critical process, and jets are the signs that a star is still being built. As stars grow, they enter the main sequence, where hydrogen fusion dominates, and this phase defines their identity, whether they burn cool and red, or hot and blue. Red dwarfs, the smallest stars, are faint but incredibly long-lived. Some may outlast the universe itself, burning slowly for trillions of years. Blue giants are the opposite, vast and bright but fleeting, consuming fuel so quickly that they vanish within a few million years. Variety is the rule, and variety gives galaxies both their steady glow and their brilliant fireworks. Astronomers use the Hertzsprung-Russell diagram to classify stars, placing them by temperature and luminosity, and this map reveals the paths stars take through their lives. The main sequence is the Great Band, where most stars sit, while giants and dwarfs form other branches. Recent surveys have mapped thousands of stars onto this diagram, each one a dot in a cosmic family portrait. Dots may seem small, but together they show how matter obeys rules, and rules give us the confidence to predict. Yet, even in prediction, surprises emerge. Recent observations have found stars in binaries trading mass, reshaping one another's futures, sometimes stripping gas, sometimes merging into a single massive object. These interactions make new supernovae, new variables, and even new black holes, rewriting what we thought were individual fates. Think of two people in conversation and how each shapes the other's thought. Stars in pairs do the same, changing courses by their exchange. Exchange itself is a universal process, and in exchange, even solitary objects reveal connection. Beyond the romance of images, these discoveries remind us that star formation is not abstract. It is the story of our own origin. Because every atom in our body was forged in such furnaces. Calcium in our bones, iron in our blood, carbon in our flesh. All of it was cooked in stars that lived long before Earth. When those stars died, they cast their ashes across space, and those ashes clumped into clouds that formed the solar system. We are literally star material, and the truth of that phrase never loses its force. Recent Webb results even show supernova remnants in detail, mapping how heavy elements are distributed, how they mix into clouds, and how those clouds become seeds for new generations. One image of Cassiopeia. Revealed knots of oxygen and sulfur glowing in filaments marking the last breath of a dead star. And those filaments are what someday build planets. Supernovae are violent, but their violence is generous, because without them, there would be no rocky worlds. Worlds themselves are built from death, and death, in this sense, is creation. Even the smallest stars carry stories. Brown dwarfs, sometimes called failed stars, glow faintly in infrared, their masses too low to sustain true fusion. Yet Webb has revealed pairs of such dwarfs adrift in space. These lonely objects remind us that the line between planet and star is blurry, and that categories are tools, not absolutes. Seeing them is like finding forgotten notes between chapters, reminders that the cosmos writes more variations than we imagine. Variation is its own lesson, that nature values abundance, and abundance ensures resilience. So when you gaze at the night sky and see points of light, know that you are seeing both the present and the past, because stars we see tonight may have died long ago. Their photons have crossed space, traveled for hundreds or thousands of years, and only now touch your eye, a meeting delayed yet faithful. The light does not know you, yet it meets you as if it were meant to, and in that meeting lies something personal. Personal in this case means that the cosmos is not distant, but woven into your moment. Stars that live for billions of years eventually reach their limits because fuel is not infinite, and even the most steady fusion must someday end. And when it ends, the story shifts from quiet burning to dramatic transformation. Our sun, for instance, will become a red giant in about 5 billion years, swelling so wide that Mercury and Venus will be consumed, and Earth itself may be baked or engulfed before the final collapse. The change occurs because when hydrogen runs out, the star must burn helium, and this pushes against gravity in new ways, reshaping the balance of forces. The outer layers expand, while the core tightens into heavier fusion. Expansion turns the once stable star into a swollen beacon, and expansion is also a sign that the calm of the main sequence is over. When the helium is spent, lower mass stars like the Sun will shed their outer shells, creating glowing planetary nebulae, clouds of colourful gas lit by the hot core left behind. Despite the name, these nebulae have nothing to do with planets. The term was coined by early astronomers who saw round shapes in their telescopes. The core that remains becomes a white dwarf, an Earth-sized body of degenerate matter, where electrons hold back collapse despite gravity, glowing faintly as it cools over trillions of years. Faint though it may be, a white dwarf is still dense beyond imagination, and dense is the correct word. A teaspoon of its matter could outweigh a mountain. Recent studies of white dwarfs have revealed planetary debris circling them, proving that systems survive even stellar death, with asteroids and remnants torn apart into dusty disks. In some cases, astronomers have detected metals in the atmospheres of these dwarfs, signatures of swallowed planets, showing us a glimpse of what might await Earth. It is not tragedy, but continuation, for the elements of those planets are not lost. They are mixed into the wider galaxy, ready for recycling. Recycling is the key word, because the cosmos wastes nothing, and waste in astronomy is simply raw material for another age. For stars much more massive than the Sun, death is far less gentle, because their cores grow hot enough to burn heavier elements, stepping from carbon to oxygen, from silicon to iron. Iron is the final barrier, because fusing iron consumes energy rather than releasing it, and that fact brings the balance to collapse. Gravity then wins completely, crushing the core in a fraction of a second, while the outer layers rebound in a catastrophic explosion, a supernova bright enough to outshine entire galaxies. Explosions like this scatter the heavy elements, and explosions like this are why planets and life can exist. Recent supernova observations with Webb and Hubble have shown fine details in the debris, mapping how oxygen, sulfur, and iron spread, and revealing asymmetries in the blast that models now must explain. Cassiopeia A, imaged in mid-infrared, glows with intricate filaments, each marking gas flung outward, each glowing with specific elements, and the clarity is sharper than any previous generation could dream. These images are more than art, they are forensic evidence, snapshots of the precise moments when stars turned themselves inside out. Forensics in this sense means piecing together cores from debris, and debris is the record of cosmic violence. The collapsed cores of massive stars become neutron stars, or black holes, depending on the mass left behind after the explosion. Neutron stars are among the strangest objects known, packed so tightly that protons and electrons merge into neutrons, leaving a sphere the size of a city but with more mass than the Sun. Their density is so extreme that a teaspoon of matter would weigh billions of tons, and the surface is more alien than any fiction. Alien here does not mean extraterrestrial, it means beyond normal comparison, and beyond is the best way to describe it. Some neutron stars spin rapidly, sending beams of radio waves like cosmic lighthouses, and these are known as pulsars, their precise ticking used as natural clocks across the galaxy. Recent discoveries include pulsars in binary systems with white dwarfs, where the dance of gravity allows us to test relativity to extraordinary precision. One newly measured pulsar in a dense cluster showed its orbit precessing exactly as Einstein predicted, and this confirmation adds to a century of unbroken tests. Confirmation after confirmation may sound repetitive, but each one tightens the net, leaving less room for alternative ideas. Other neutron stars reveal themselves as magnetars, with magnetic fields trillions of times stronger than Earth's, so strong they could erase credit cards from half the distance to the Moon. These bursts sometimes detected as sudden flares of X-rays and gamma rays. Astronomers continue to watch for fast radio bursts, millisecond-long flashes of radio light that may come from magnetars or from other still unknown processes. Webb and other telescopes are beginning to pinpoint the origins of these bursts, tying them to distant galaxies and specific environments. Origins matter because they give context, and context is how a mystery slowly becomes a field of study. When mass is greater still, collapse leads past neutron stars into black holes, where gravity overwhelms every other force and even light cannot escape. This is the most extreme end of stellar death. Some of these stellar black holes have been measured through gravitational waves, merging into larger bodies and releasing more energy than all the stars in the universe at that moment. These mergers leave behind ringing space-time, a final echo we can detect on Earth, and those echoes are already catalogued by dozens. Catalogues may sound dry, but each one is a story of two stars dying together, and together they leave behind a deeper silence. Recent LIGO detections even show black holes with unexpected masses, too heavy for normal stellar deaths, suggesting they may have formed through earlier mergers of smaller holes. These hierarchical chains are cosmic genealogy, family trees of collapsed objects that build up over generations. By following these patterns, astronomers learn how stars in dense clusters evolve and how repeated collisions make new extremes. Extremes are where physics is tested hardest, and tests in this regime may reveal cracks in our understanding. There is also the mystery of pair instability supernova, explosions so violent that the star is completely destroyed, leaving no remnant. Models predict them for the most massive stars, yet clear examples are rare. Webb has been tasked with hunting such events, and its infrared eyes are well suited to catch the fading afterglow. If found, these supernovae will reveal how the earliest giants seeded the universe with heavy elements, and how quickly the first galaxies were enriched. Enrichment is not an abstract term. It is the reason carbon and oxygen exist, and existence itself depends on such explosions. When we reflect on stellar death, it is tempting to think only of endings, but the cosmos writes continuity, not conclusion. Every ending feeds the next beginning. A supernova's debris becomes gas clouds, a white dwarf's cooling becomes cosmic background heat, a pulsar's ticking becomes a clock for astronomers. Even a black hole, silent as it may be, becomes a laboratory for testing gravity and a beacon through its mergers. Laboratories and beacons are not endings, they are transformations, and transformations are the real story. For humans listening late at night, the idea of death turned into birth can be comforting because it mirrors our own fears. We fear endings, but endings are part of the fabric of change. Astronomy shows that loss is never final, and that finality is not a law of nature. Stars die, but their matter lives on in clouds and planets, in bones and oceans. And so we are the continuation of deaths that happened long before Earth. Knowing this reshapes grief, because it shows that endings feed beginnings, and knowing this lets us accept impermanence with more calm. Astronomers continue to measure supernova rates, and the data suggest that galaxies produce them at steady intervals, each one feeding the interstellar medium with metals, making the cosmos chemically richer over time. Recent Webb images of distant supernovae confirm that explosions happened even in the first billion years, and those explosions built the first seeds for rocky worlds. To see them so early is to see the urgency of creation, and the urgency tells us that galaxies wasted no time in making the ingredients of life. Life, therefore, has been possible almost from the beginning, and beginning itself carries more possibility than we once believed. Every insight we gain from the cosmos comes through light, because no other messenger travels so far and so faithfully. And even when gravitational waves and particles join the story, light remains the first voice. Photons have crossed billions of years to reach us, each particle carrying the record of where it began, each signal unaltered except by the spaces it crossed. When you step outside and look up, every star that touches your eye has given you a direct gift, a photon that began its journey before you were born and which ends inside your retina. Journey and gift are not metaphors here, they are facts, and facts themselves can feel intimate when carried in light. Astronomy is built on spectra, the splitting of light into colours, and in those colours we find patterns, dark lines where atoms absorbed their preferred energies, bright bands where gases emitted them back. These spectral lines are the alphabet of atoms, and they are the most precise codes we know, because hydrogen always leaves the same signature, helium the same, oxygen the same. By reading these codes, we know what stars are made of, what clouds contain, and even what planets breathe, the entire language of chemistry carried by light. Language here is literal, for photons speak, and speaking is what allows matter across space to announce itself. Recent advances with the Webb telescope have refined these spectra, especially in the infrared where dust is transparent, revealing molecules in planetary atmospheres and the details of star-forming clouds. One striking spectrum showed methane and carbon dioxide on a distant world, while another revealed water vapor high in its sky, and these detections are the beginning of habitability studies. Though no single line proves life, each line is a hint, and hints are how discovery begins. Step by step, cautious but meaningful. Meaning is always larger than the measurement itself, because the context of a faint line is the possibility of another world. Light also bends, and in that bending lies another tool, gravitational lensing, where mass curves space so that photons follow arcs instead of straight lines. Clusters of galaxies act as lenses, turning distant galaxies into stretched arcs, magnifying them so that we see deeper than we otherwise could. Recent Webb lensing images have revealed galaxies less than 500 million years old, far more developed than expected, forcing revisions of galaxy formation models. Revisions may sound unsettling, but they are simply adjustments, and adjustments keep the map aligned with reality. Spectra and lensing together form a dialogue. One tells us composition, the other reveals structure, and both combine to paint a fuller picture of the universe. For example, when a lensed galaxy's light is spread into a spectrum, we can measure not only its distance, but its star formation rate. This allows us to compare early galaxies with modern ones and to see how quickly stars formed in the first billion years. Quickness is not trivial. It is a clue, and clues are what keep astronomers attentive. Another powerful method is polarization, where light's orientation reveals the structure of magnetic fields, as we saw near black holes where the EHT recorded flips over years. In the wider cosmos, polarization maps show dust alignment, which in turn reveals the threads of magnetic fields in clouds. Recent Planck and Webb observations have traced these threads in exquisite detail, showing how magnetism shapes the birth of stars, resisting collapse in some regions, guiding it in others. Threads of magnetism tie into the larger web, and webs of such forces remind us that gravity is not alone in shaping destiny. Even the faintest cosmic glow is read through light, the cosmic microwave background, the relic radiation from the hot early universe, stretched to millimeter waves after billions of years of expansion. This background is uniform, but it carries subtle ripples, and those ripples are maps of the seeds of galaxies. Recent refinements continue to measure its anisotropies, giving us sharper estimates of matter content, dark energy, and the curvature of space. Curvature is not an abstract shape, it is the way geometry itself bends, and bending is why expansion is more than simple motion. Light also redshifts, stretching toward longer wavelengths as galaxies recede, and that shift tells us their velocity, Hubble's discovery that expansion is universal. Recent Webb confirmations of redshifts above 13 push us closer to the dawn of galaxies, capturing light that has stretched for over 13 billion years. These extreme redshifts are not just numbers, they are boundaries of vision, and each new detection shifts the boundary further. Boundaries like this are fragile, always ready to move, and fragility is what makes them so exciting. Astronomers also use light curves, the steady changes of brightness in stars, to detect planets or measure pulses. Transits reveal planets, supernovae reveal explosions, pulsars reveal timing. Webb and ground-based telescopes have refined light curves to such precision that they detect atmospheric signatures during a planet's transit, a dip in light combined with spectral shifts. Every curve is a story of motion, every dip a story of presence, and together they let us find worlds too faint for direct imaging. Presence matters, because once a world is detected, we can ask what kind of air it carries. The James Webb Telescope has also imaged star-forming regions in detail unseen before, revealing jets of plasma and shocks of gas, each glowing in infrared signatures. In Carina, Orion, and other nebulae, Webb has seen young stars with disks already forming, and in those disks, shadows of planets. This is not theory, it is visual evidence that planet formation begins early, and evidence that we are watching the process itself. Watching here is extraordinary, for it turns speculation into observation, and observation becomes history written in light. The future of light studies lies in spectroscopy at ever greater resolution. Instruments already planned will measure faint lines with unprecedented accuracy, letting us test whether constants like the fine structure constant have always been the same. If they shift even slightly across billions of years, that would be a new physics, a change in the very rules that atoms follow. Such possibilities remain unproven, but the fact that light allows the test is remarkable, and remarkable is itself enough to justify the work. Tests like these are why astronomy is never only about stars, but about the laws that guide everything. There is also neutrino astronomy, though light still dominates. Yet even here, detectors await the flash of neutrinos from a nearby supernova, particles that escape before photons, carrying early warnings. The 1987 A supernova already gave us a brief signal of neutrinos, proving that stars collapse with invisible shouts before light emerges. Next time such a nearby event occurs, instruments will be ready, and they will tell us how collapse unfolds in real time. Time in this sense is precious because we rarely catch processes as they happen, and rarely makes the anticipation stronger. Even more subtle are cosmic rays, particles launched by supernovae and jets, slamming into Earth's atmosphere. Yet even they tell us about distant accelerators. Light, neutrinos, and cosmic rays together form multi-messenger astronomy, and gravitational waves now complete the set. Recent events have been observed in both gravitational waves and light, tying mergers to gamma-ray bursts, tying bursts to kilonovae. Kilonovae themselves are stellar forges making gold and platinum, and gold in your jewelry may have been cast in one. For a listener tonight, the technical detail can fade and the image can remain. Photons crossing voids, spectra carrying codes, arcs of lensing, ripples of background glow, sudden dips of transit curves. These are not only data, but whispers, and in those whispers lies a sense of continuity. We are connected to stars and galaxies by light. We are connected by the same laws that govern hydrogen and helium. Connection is the quiet reward of astronomy, and connection is what allows distant events to matter here. Time is the quietest force in the universe, and yet it is the one measure that frames every discovery, for without it, distance and change would make no sense. We live inside time as fish live in water, so constant that we forget it, so present that we never step outside. But astronomy reminds us that time is not simple. Entropy gives time its arrow, the fact that disorder grows and cups shatter but do not repair. And this is why we know the past from the future. Arrow is the chosen word because time points us toward memory on one side and uncertainty on the other. In human lives, we know time as clocks, as the calendar that guides work, and as the heartbeat that insists each second has passed. In the cosmos, time is stretching and bending, shaped by gravity, so that a second near a black hole is not the same as a second here. Einstein's relativity showed that time is not absolute, but a dimension braided with space, one that slows where gravity deepens and runs faster in open skies. Slowing and quickening are not illusions, they are measurable, and measurable is why satellites must account for relativity every day. Recent tests with atomic clocks have proven this again, with devices so precise that a shift of a few centimeters in height makes a difference. One clock on a mountain ticks faster than one in a valley. These clocks are now sensitive enough that they can measure the curve of Earth's gravity directly, making them tools of geodesy, measuring planet shape through time itself. This is the same principle that makes GPS possible, because signals from satellites must adjust for relativity, or your location would drift kilometers in minutes. Adjustment here is not philosophy, it is engineering, and engineering proves the theory every day. In the larger cosmos, time stretches with expansion, and the redshift of galaxies is proof that intervals of light have grown, each wave stretched as space itself expands. This stretching means we see galaxies not as they are, but as they were, because the light has taken billions of years to reach us. Look at a distant quasar, and you see a signal from when the universe was young, from a moment long before Earth had formed. Moments like these remind us that the past is visible, but the present is always local. Entropy adds another layer, why time feels one way. A hot cup of tea cools, but it never warms itself, because energy spreads, and spreading makes states less ordered. The universe too drifts toward more disorder, with stars burning fuel and galaxies spreading apart. And yet, in small corners, order appears, like planets and life. It is not that entropy fails, it is that local pockets borrow order for a while, before giving it back to the flow. Borrowing gives us our temporary world, and temporary is why life feels fragile but meaningful. Astronomers now ask whether the arrow of time is linked to cosmic expansion, whether the growth of space gives the arrow its strength, or whether entropy alone defines it. Some theories suggest the universe could contract in the far future, and with contraction, perhaps time itself could reverse. This is speculation, but it is rooted in the same laws that govern stars, and it shows how the laws leave room for imagination. Imagination is not against science, it is the seed of it, and seed is the start of discovery. When we compare human time to cosmic time, the difference is overwhelming, because lifetimes are measured in decades, while stars live for billions, and galaxies evolve across ages beyond speech. Yet even here, relativity gives us ways to compare, because clocks can slow for astronauts near black holes, while distant observers watch them freeze. This is not fantasy, but calculation, and recent images of jets near black holes show particles slowed in our view, slowed by gravity itself. Slowing here is a reminder that perspective matters, and perspective is why time cannot be thought of in isolation. The Event Horizon Telescope and Webb together now let us see motion in regions where relativity dominates and where time bends. Each flicker in Sagittarius A is a living test of Einstein's predictions. If we can stitch those flickers into movies, we will literally watch time's flow near a horizon and confirm whether our models hold. Even gravitational waves are clocks, their ripples encoding the frequency of orbit, the rate of inspiral, and the moment of collapse. Frequencies like these are measured in hertz, but each one is a cosmic tick, and ticks build into a record of time. There is also cosmic time as defined by radioactive decay, elements that serve as natural clocks. Uranium in rocks, isotopes in stardust, all of them counting quietly. These clocks tell us the ages of planets, the ages of meteorites, and even the timescales of the first heavy element production. Recent studies of ancient stars with unusual chemical abundances show traces of uranium. giving direct measures of their ages over 13 billion years. 13 billion years is not abstract. It is the lifetime of the cosmos itself, and lifetime is what such clocks quietly confirm. What does this mean for us? It means that time is not only a measurement, but a landscape. One where seconds differ depending on place, where billions of years are as natural as heartbeats. It also means that every human moment is small but not irrelevant, because even stars are small in the context of galaxies. The fact that time flows differently under gravity tells us that experience is relative, and relativity is the deeper rule. Deeper still is the mystery of why time flows at all, and mystery is why it remains both a scientific and personal question. Planets are the shadows cast by stars, yet they are also the worlds where stories unfold. For while stars burn and galaxies drift, it is planets that host the textures of soil, water, and air. Our solar system gives us the template, with rocky bodies near the sun and gas giants farther out, a pattern shaped by physics but filled with individuality. Mercury is a scarred rock, Venus a suffocating oven, Earth a temperate sphere where life emerged, Mars a frozen memory of rivers. Memory and scar are both lessons, reminders that planets are fragile, and fragility is what makes them precious. Beyond the frost line, giants like Jupiter and Saturn hold storms and moons. Uranus and Neptune hold secrets of ice, each one shaping its system of satellites and rings. Moons like Europa and Titan are worlds in their own right, with oceans beneath ice and methane lakes reflecting alien skies. The solar system is therefore a layered archive, each planet a chapter, each moon a page, and our spacecraft have begun reading them. Reading has already changed our sense of home because Earth is no longer the only place where oceans might exist, and oceans are central to our search. Planetary formation begins with dust and gas around newborn stars, where grains stick together, collide, and grow, building from pebbles to rocks, from rocks to planetesimals, from planetesimals to planets. Gravity sculpts these building blocks, and collisions both destroy and create. Some fragments lost, others added until stable orbits emerge. Recent Webb images of protoplanetary disks have revealed gaps and rings likely carved by forming worlds, the first photographs of planets mid-birth. Birth is therefore not a hidden process anymore, and birth, seen directly, confirms decades of theory. Exoplanet discoveries have expanded this story far beyond our system, with thousands confirmed, each one a unique experiment. Hot Jupiters grazing their stars, super-Earths circling inhabitable zones, rogue planets drifting alone. The Kepler mission began this revolution, but Webb and ground observatories now add detail, probing the atmospheres of a few chosen worlds. Spectra reveal molecules, clouds, even hazes, painting each sky with tentative chemistry, and each chemistry with implications. Implications reach to the core of curiosity, for air that holds water or methane hints at possibility, and possibility is what keeps us looking. Recent results on K2-18b have stirred debate, with methane and carbon dioxide detected, but the special molecule dimethyl sulfide still unconfirmed, an example of hope balanced by caution. Webb's precision has confirmed the major gases, but the biosignature remains a question, one that future data will address. Even without life, such signals are extraordinary, because they prove that exoplanet atmospheres can be measured with clarity, and clarity is the doorway to truth. Doorways like this rarely open in science, and when they do, each step must be careful, for the path is fragile. TRAPPIST-1e and its siblings remain prime targets, rocky worlds orbiting a cool star only 40 light-years away, where habitability may be tested. Webb has begun analysing their light, though signals are faint and results are not yet final. But patience here is key, for these planets may be our best shot at near-Earth analogues. Already hints of atmospheres have been sought, though some data suggest erosion from stellar flares may strip their air. Erosion is not failure, it is context, and context tells us which worlds can hold life and which cannot. Hot Jupiters remain another class of fascination, with winds circling at thousands of kilometers per hour and blazing temperatures hotter than some stars, their skies filled with exotic molecules. One Webb spectrum revealed sodium and water vapor in a giant's atmosphere, and even cloud decks forming high above its storms. Such results may not point to habitability, but they point to physics, and physics in extreme cases tests the limits of theory. Limits are where growth begins, and growth in astronomy always follows the surprise. Some exoplanets orbit dead stars, including pulsars, where planets circle under beams of radiation, worlds as strange as science fiction, and yet real in the catalogues. Others drift freely between stars, rogue planets, unbound, wandering without a parent sun, discovered by their faint heat signatures. These loners remind us that stability is not the rule, that systems often eject members, leaving them to wander. Wandering is itself a kind of existence, and existence without light is still existence. Closer to home, our own planets remain alive with discovery. Mars continues to reveal dried rivers, salts marking lakes that vanished billions of years ago, and rovers still probe for organic molecules. Europa's hidden ocean may soon be tested by the Europa Clipper mission, its surface streaked by cracks that vent salty spray. Titan's methane lakes are another frontier, where NASA's Dragonfly drone will one day fly through hazy skies, sampling chemistry as alien as any dream. Dreams here are tangible plans, and plans remind us that discovery is ongoing. Even Earth participates in discovery, with satellites monitoring our own air, finding human fingerprints of carbon dioxide and methane, and teaching us that planets are fragile systems. Studying Earth teaches us to study others, because climate models are universal and atmospheres respond to the same laws everywhere. When we read spectra of distant worlds, we practice first on our home. Home itself becomes the reference, and reference makes the strange familiar. Recent findings have even suggested volcanic activity on exoplanets, where sulfur dioxide in spectra points to ongoing eruptions, a sign that geology as well as atmosphere can be detected. Such detections hint at dynamic interiors, planets alive with heat, shaping their surfaces as Earth does. This is profound, for it means we are not only reading skies, but landscapes, even from light years away. Landscapes themselves may never be walked, but landscapes glimpsed are still landscapes known. One of the most haunting possibilities is that of detecting oxygen, a molecule tied closely to biology here, yet not unique to it. Caution is needed, for oxygen can be made abiotically as well. Still, the day a clear oxygen line is seen in a rocky world's spectrum will be a turning point. Even if biology is not confirmed, the presence of such a signal will reshape the search and reshape how we define life. Life itself may be broader than we imagine, and imagination may be the only tool broad enough to match. Our instruments are only beginning this work. In the coming decades, larger telescopes on the ground and in orbit will extend spectra to smaller planets, perhaps Earth-like worlds orbiting Sun-like stars. The extremely large telescope in Chile will soon gather enough light to probe exoplanet skies, and missions like l'Oeuvre may one day image pale blue dots directly. These projects are long-term, but so was Hubble, so was Webb, and patience has already given us returns. Patience is the lesson astronomy never stops teaching, and lesson is what discovery always offers in return. Moons are often called companions of planets, but in truth they are worlds in their own right, each carrying stories as rich as their primaries. Europa, one of Jupiter's great moons, hides an ocean beneath its icy crust, an ocean larger than all the seas of Earth combined. Cracks on its surface leak salts and vapor, geysers that may spray into space, and instruments already aboard spacecraft have caught signs of this water. Water is the one ingredient we always chase, and water makes Europa a prime target in the search for life. The upcoming Europa Clipper mission will fly close dozens of times, sampling plumes and mapping the icy shell, searching for chemistry that hints at habitability. If microbes exist anywhere beyond Earth, Europa is one of the most likely havens, because energy from tidal forces keeps the ocean warm. Gravity from Jupiter pulls on Europa's interior, flexing it like a ball of dough, and that flexing makes heat, enough to melt what would otherwise be frozen solid. Flexing tides are engines hidden in silence, and engines like this give even cold moons a chance at activity. Enceladus, a smaller moon of Saturn, also has plumes that spray into space, fountains of water vapor and ice grains detected by the Cassini mission. Those grains carried traces of salts and even simple organic molecules, direct evidence that chemistry at least begins in its ocean. The geysers erupt from cracks near the pole, lit by sunlight into shining plumes that stretch for hundreds of kilometers. Plumes like these are cosmic invitations because they make sampling easier, and invitations like this may not come often. Titan, Saturn's largest moon, is even stranger, with lakes of methane and rivers of liquid ethane, a world colder than Antarctica but still sculpted by weather. Its orange haze hides the surface, but radar has mapped shorelines, dunes, and branching channels, a landscape eerily familiar though made of alien chemistry. NASA's Dragonfly mission will one day fly there, a drone buzzing over dunes and lakes, searching for prebiotic processes. Flying in that thick atmosphere will be easier than on Earth, and flight itself will be the first on a world so distant. Recent Cassini data showed Titan's dunes may be built from organic grains, complex molecules that settled from the air, and this raises questions about chemistry heading toward complexity. Though Titan is too cold for water-based life, its methane cycles are a living analogy, showing that climates can run on other fluids. Studying Titan stretches our imagination, showing that planets and moons need not follow Earth's template. Imagination is not indulgence here, it is preparation, and preparation is what science always requires. Other moons surprise us too. Ganymede, the largest in the solar system, has its own magnetic field, a sign of a liquid metallic core. Callisto's battered surface holds the oldest craters, a frozen record of impacts across 4 billion years. Io, in contrast, is violent and active, covered in sulfur volcanoes driven by tidal heating, lava lakes glowing red under Jupiter's gaze. Volcanoes, they erupt constantly, making Io the most geologically active body in the solar system. Moons remind us that size does not decide richness, that small bodies can be more varied than planets, and their diversity makes them essential to exploration. In recent years, telescopes and spacecraft have spotted faint oceans beneath other icy bodies, from Ganymede to Pluto's heart, suggesting that hidden seas may be common. Pluto, once called a planet, revealed a smooth plain of nitrogen ice in the shape of a heart when New Horizons flew by. Plain though it looked, convection cells there reveal motion, and motion means the world is not dead. Dwarf planets like Ceres also carry surprises, with bright spots of salt shining on their surface, residues of briny water that once seeped upward. The Dawn spacecraft found these bright deposits and confirmed that even small bodies can remain active. This discovery matters because it blurs the line between asteroids and planets, showing that geology thrives even in unlikely places. Lines we draw in categories often dissolve, and dissolving is part of growth. Asteroids themselves are leftovers, fragments of the solar system's birth, rubble that never formed into full planets, but rubble that still holds records. Missions like OSIRIS-REx have brought back samples from Bennu, a carbon-rich asteroid filled with organic compounds. Preliminary analysis shows amino acids and complex molecules, proving that the seeds of life were scattered in stone. Seeds like this may have helped Earth itself, and helped is the simplest word for one of the deepest ideas. Recent missions to Ryugu and Bennu suggest these asteroids are fragile, more like piles of gravel than solid rock. Their low density meaning they could break apart easily. Understanding them matters not only for science, but for defense, because asteroids cross Earth's path. Planetary defense requires knowing how to deflect such bodies, and the DART mission already tested nudging one asteroid off course. Deflection worked, proving humanity can act, and acting early could one day protect us. Comets are another archive, icy bodies from the outer system that glow with tails when near the sun, their ice is releasing gas and dust in long streams. Rosetta's mission to Comet 67P revealed organic molecules and cliffs of black rock, showing us a world both fragile and ancient. Comets may have delivered water to Earth or even the first organics, carrying chemistry across billions of years. Delivery of life's ingredients is no myth, it is plausible, and plausible ideas guide the search. Even now, new small worlds are discovered in the Kuiper Belt, with orbits that hint at unseen giants, a possible Planet 9 tugging on their paths. Though still unconfirmed, such an object would be a revelation, rewriting our map of the solar system. Searches continue, with telescopes scanning the sky for faint light and simulations predicting possible orbits. Whether it exists or not, the hunt itself teaches, and teaches us how models meet evidence. Moons and small bodies are not side stories, they are central to the plot, because they carry the chemistry of life and the history of formation. They remind us that wonder comes in all sizes. Recent missions have shown how even kilometre-wide rocks hold clues, and how frozen surfaces can hide oceans as vast as Earth's. These revelations reshape our focus, pulling attention from giants to the minor, showing that the smallest worlds can carry the largest secrets. Focus like this expands what counts as important, and importance is always broader than we think. For the listener tonight, it may be comforting to think of these worlds as neighbours, strange but familiar, moons with seas, comets with chemistry, asteroids with seeds. They exist quietly, orbiting in darkness, untouched except by the light of distant suns. And yet they matter because they remind us that life may not need a perfect world to start. Perhaps oceans under ice are enough, perhaps chemistry on comets is enough, Perhaps the ingredients are scattered so widely that the odds were always in favor. Enough may be the most hopeful word in astronomy, because enough means possibility is never rare. The more we learn, the more we realize how much is hidden, because most of the universe is made of matter and energy we cannot see, and this absence is as real as any light. Dark matter is the name given to the unseen mass that bends galaxies, while dark energy is the name given to the unseen force that pushes space, and together they make up 95% of everything. We see their effects, but not their substance. We trace their influence, but not their form. And this is both unsettling and inspiring. Invisible does not mean imaginary, it means the universe is still unfinished in our maps, and unfinished maps are invitations to keep moving. Evidence for dark matter began with galaxies themselves, because stars at the edges were moving faster than visible gravity allowed. Their orbits demanded more mass than telescopes could see. Vera Rubin's work in the 1970s confirmed these curves, showing that rotation stayed flat instead of falling, as if halos of invisible matter surrounded galaxies. Since then, gravitational lensing has confirmed the clumps, bending light from distant sources in ways that match unseen mass. Clumps like these are not guesses, they are measurements, and measurements keep pointing toward the same conclusion. Recent lensing maps from Webb and other observatories have shown even finer structure, with subhalos inside clusters, proving that dark matter is not smooth but grainy. This detail is crucial because it hints at the nature of the dark particle, whether it is cold and slow or warm and fast. Cold dark matter models predict these fine clumps, while warm models predict smoother flows, and the data so far favor the cold picture. Cold and warm here do not mean temperature, they mean speed, and speed is how physics distinguishes the invisible. Experiments on Earth search for direct interactions, with detectors buried deep underground or in icy mines, hoping to catch a rare collision between a dark particle and normal matter. So far, no confirmed signal has been seen, though occasional hints have sparked debate, and every non-detection sharpens the limits. Other searches look for annihilation signals in the sky, photons or neutrinos born when dark particles collide, but these too remain quiet. Quiet is frustrating, but it is also a kind of answer, because it rules out what the particle cannot be, and ruling out is progress. Dark energy is stranger still, a pressure that drives cosmic acceleration, discovered in the 1990s through distant supernovae, when astronomers expected slowing expansion but found the opposite. This acceleration remains unexplained, described only by a term in equations called the cosmological constant, and by the name dark energy. It behaves like a steady push in the vacuum of space, and its density seems nearly constant across time. But why it has the value it does is unknown. Unknown is not failure, it is possibility. And possibility is where science breathes. Recent galaxy surveys keep measuring dark energy's influence, mapping baryon acoustic oscillations and gravitational lensing patterns. And so far, the push remains steady. Some models suggest it could change with time, that its pressure might evolve, while others hold it fixed, a constant. Webb, Euclid, and other telescopes are now feeding data into this debate, tracing how structures grew and how voids widened. Voids are as telling as clusters, because emptiness too responds to forces, and emptiness is half the story. One mystery is why dark energy appeared when it did, because acceleration began only a few billion years ago, not at the very start. This coincidence of timing is unsettling. It seems tuned, as if the density of matter and energy crossed a balance point exactly when galaxies matured. Some physicists wonder if this coincidence hints at deeper rules, or if it is simply how the numbers fall. Coincidence itself is a dangerous word because it tempts us to look for design, while design is not yet science. Speculative ideas like the multiverse emerge here, suggesting that our universe is only one bubble among many, and that others may have different constants, with ours tuned for life because we are here to ask. This is called the anthropic principle, and though unsatisfying, it offers one answer: that we exist in the kind of universe that allows existence. Evidence for such other universes is scarce, but quantum theory and inflation models leave openings where they might be real. Openings are not proofs, but they are enough to keep thinkers awake, and awake is the state where science begins. Closer to testable ground, some models suggest dark matter might be axions, ultralight particles that slip through matter, while others propose WIMPs, weakly interacting massive particles. The Large Hadron Collider and underground detectors are both chasing these possibilities, though none have yet appeared. Meanwhile, alternatives like modified gravity suggest perhaps no particle exists, that Newton and Einstein's laws need tweaks, though observations often prefer the particle view. Tweaks are tempting, but every new dataset strengthens the case for something unseen rather than new laws alone. Gravitational waves add another angle, because their ripples may probe dark matter halos or reveal exotic objects that mimic them. If black holes made of primordial dark matter exist, they might explain at least some of the invisible mass. So far, signals are inconclusive, but detectors are improving, and the coming decades may bring clarity. Clarity is the most precious result, and clarity comes slowly in this domain. Meanwhile, theorists test the cosmological constant with vacuum energy calculations, but the predicted value is trillions of times too large, one of the worst mismatches in physics. Why the vacuum does not push harder is unknown. Why it pushes at all is equally unknown. This mismatch is called the cosmological constant problem, and it remains one of the deepest gaps in theory. Gaps like these are frustrating but fertile, and fertile soil is where revolutions take root. In daily life, it may seem far from relevant, but knowing the universe is mostly dark changes our sense. It means that what we see is only the surface of a vast, unseen structure. Galaxies, stars, and planets are only 5% the visible crust of a hidden mass. To accept this is to accept humility, that our instruments reveal much but not all, that sight is limited, that limits are invitations. Invitations to imagine and to measure again, and imagine again, until the unseen begins to show itself. Recent surveys have mapped dark matter more directly by using weak lensing of millions of background galaxies, turning small distortions into maps of halos and filaments. These maps align well with simulations, though small tensions remain, such as the exact clumpiness of structures. If structures are less clumpy than expected, this may point to warm particles or to new physics beyond cold models. Tensions here echo the Hubble constant debate, small mismatches that may one day be cracks, and cracks are how light gets in. Dark energy surveys now use supernova samples in the thousands compared to dozens in the 1990s, and the patterns are consistent. Acceleration persists. The push is steady. Euclid has begun releasing maps of galaxies, measuring how their clustering evolves, and Webb extends this to high redshifts. So far the story holds. The universe accelerates. Its fate is expansion without end. End here means heat death, a slow fading where stars die and galaxies drift beyond sight, and fading is the ultimate arrow. Yet the mystery remains whether acceleration could change, whether dark energy might weaken or even reverse, leading to collapse instead of heat death. These scenarios are not ruled out, though current data favor constancy and current data carry weight. If reversal occurred, the universe could one day contract, galaxies pulled back, time itself perhaps mirrored. Mirrored possibilities are speculative, but speculation is not forbidden, and forbidden is not how science grows. These mysteries can sound abstract, but they are part of our story, part of the context in which Earth exists. Knowing that most of reality is dark changes how we view the light, making every photon rarer, making every spectrum more precious. Even if answers come slowly, the process itself is inspiring because it shows that humans can admit ignorance and still search. Searching is its own dignity, and dignity is what astronomy offers most gently. The universe is not a finished book. It is a story still being written. Each observation adding new lines, each telescope revealing words that were invisible before. We have learned to listen across every wavelength, to stitch photons into maps, to measure waves in space-time itself, and yet most of reality remains unseen. Dark matter still hides its face. Dark energy still hides its source. And these silences remind us that mystery is not an obstacle, but a companion. Companions like this guide us forward, and guidance is often as important as answers. Webb has shown us galaxies too mature in the early universe, clusters more massive than models allowed, and each surprise bends our timelines into new shapes. Euclid has begun mapping the faint patterns of galaxy clustering, tracing how dark energy has pulled space apart over billions of years. The Event Horizon Telescope continues to sharpen the portraits of black holes, their horizons shifting, their polarization flipping like restless flames. Flames may fade, but horizons stay. And staying is how we keep learning from them. Recent gravitational wave detections have revealed black holes that recoil, newborn remnants kicked away by imbalance, their motions written into the ripples we record. Neutron stars merging have given us kilonova light, gold and platinum forged in their ashes, elements that now rest in our jewelry and instruments. Fast radio bursts, once unexplained, are now tied to magnetar flares, proving that even millisecond flashes carry stories across galaxies. Flashes of this kind are small in duration, but not in meaning, and meaning is what turns noise into signal. Exoplanet atmospheres have given us their own quiet messages, with methane and carbon dioxide read in the light of distant suns, with water vapor confirmed in the skies of giants. K2-18b remains debated, its dimethyl sulfide claim still a question, but its spectrum is proof that alien skies can be tested. TRAPPIST-1's rocky worlds continue to challenge us with faint signals, some perhaps stripped by flares, others perhaps still holding air. Signals like these may feel fragile, but they are solid steps, and fragility is part of discovery's honesty. Even small missions reshape our sense of scale. Bennu's samples returned with organics. Ryugu's gravel revealed molecules that once seeded life, proving that the building blocks are common, scattered across stone and ice. The DART mission struck an asteroid and nudged its path, showing that defense is possible, that human hands can touch celestial mechanics. Europa Clipper prepares to taste the spray of Europa's ocean. Dragonfly prepares to fly across Titan's methane lakes. Preparing is its own act of discovery, and prepared missions become tomorrow's history. Stars continue to guide us. Webb has imaged nurseries where jets pierce clouds, protoplanetary disks already ringed with shadows of planets. Supernovae like Cassiopeia. A glow in mid-infrared, filaments of oxygen and sulfur revealing how elements are scattered, how galaxies are enriched. White dwarfs swallow remnants of planets, leaving traces of metals in their spectra. Proof that planetary systems outlast their suns. Proof like this connects directly to Earth's future, and future itself is part of astronomy's reach. Time remains the most elusive dimension. Atomic clocks now tick with such accuracy that lifting one by a meter changes its rate, proving relativity not in theory but in centimeters. Gravitational lensing continues to magnify galaxies, letting us see their past at redshifts above 13 billions of years before our world. Cosmic microwave background surveys refine the ripples, matching models yet leaving the Hubble tension unsolved. Tension here is not discomfort but opportunity, and opportunity is where revolutions begin. Dark matter maps grow sharper, lensing revealing hidden clumps, radio arrays tracing cosmic threads that match simulations. Yet no particle has revealed its identity, no detector has confirmed its touch. And the silence is as loud as the discoveries. Dark energy continues its push. Supernovae and galaxy surveys showing the same steady acceleration. Steady, yet unexplained, it defines our fate, and fate is the quiet word that lingers. Still, in the face of these unknowns, astronomy does not stop. Each night telescopes open their domes, each morning data arrive from probes. Gaia refines stellar positions, Webb refines planetary air, LIGO refines spacetime's ripples. The rhythm is constant. Observe, interpret, correct, repeat. Rhythm gives the field its patience, and patience gives it its power. For the listener, this long drift is not just science, but solace. To know that photons cross voids, that galaxies send us their light, is to know we are not alone in silence, to know that stars die and give us carbon, that supernovae scatter iron, is to know our bodies are continuations of their lives, to know that Europa hides an ocean, that Titan has methane rivers, is to know that the universe is generous with variation. Generosity is not a human projection here, it is a fact, and facts themselves can comfort. Even the mysteries offer comfort. Dark matter may be unseen, but its presence holds galaxies, keeps structures together. Without it, the universe would not form the shapes we admire. Dark energy may be unexplained, but its push makes space vast. Its influence gives us the long future of expansion. The multiverse may be speculation, but even the idea reminds us that laws could vary, that life is one version among many. Speculation is not weakness, it is imagination tied to physics, and imagination is what lets us breathe possibility. And so we reach the closing arc, not of the universe, but of this narration. The cosmos is unfinished, and so is our knowledge, but that incompleteness is the very reason we continue. We will keep listening to black holes flicker, to pulsars tick, to waves ring through space-time. We will keep chasing exoplanet air, mapping distant galaxies, testing constants against light billions of years old. Chasing is itself the story, and story is what the cosmos gives us in return. So as you rest tonight, remember that you are part of this fabric, that your atoms were made in ancient fires, and that the photons touching your eyes began journeys long before Earth was born. Remember that uncertainty is not emptiness, it is invitation, that mystery is not absence, but abundance. Remember that we are both tiny and vast, fragile and enduring, because our lives are the universe noticing itself. Noticing is the closest thing to meaning, and meaning is the gift we carry back from the stars. May you feel that the questions are companions, and may you feel that the cosmos itself drifts with you, not demanding answers, only offering wonder. May the discoveries of this age, Webb's galaxies, Euclid's maps, EHT's horizons, LIGO's waves, remind you that searching is timeless, that wondering is eternal. May you know that black holes and stars, moons and comets, dark matter and light, all belong to the same story, the story that includes you. Belonging is the quietest truth, and truth is what lingers when the narration ends.